Electricity. It makes us masters of our environment, yet most of us take it for granted. Deprived of it, we get a sense of what life was like more than 150 years ago, before power transformed our society and our lives. In the middle of the 19th century, a day's work was just that, labor that necessarily took place during the sunlit hours. Work itself was backbreaking, manual, mostly unaided by machinery. The arrival of night meant retreat indoors from the dangers associated with the pervasive darkness. Over the next century and a half, we took a world which had dominated us and transformed it into this. An electrified environment which responds to our every need. We control our climate, process information, and tend to our health with power that flows hundreds of miles across an interconnected transmission grid that encompasses the entire country. Electric current, the flow of charged electrons, intimately influences how we live, yet most of us understand little about how it works. In 600 BC, the Greeks first discovered that static electricity could be generated by rubbing amber. It wasn't until the 18th century, however, that Benjamin Franklin theorized that electrical fluid might be composed of particles. By harnessing this flow of electrons, or current, inventors and industrialists more than a century later laid the foundation for what would become the colossus of electrical generation, the modern power plant. It can be anything from a red-hot behemoth that once started consumes trainloads of coal without interruption for years. Or it might be a nuclear plant, incongruously perched at the edge of the shimmering Pacific Ocean. A plant that on its own produces 20% of Southern California's energy. Or maybe it is simply this, a house that generates more energy than it consumes and returns that surplus to the electrical grid for public use. A new model for the future of power plants. But whatever guise contemporary power plants take, the basics of their design and their integration into commercial and domestic life were forged more than 100 years ago in a conflict between two giants of industry and invention, Thomas Edison and George Westinghouse. The outcome of the fierce competition between these two men would ultimately dictate how electricity would be generated and transmitted. But their first battle would be waged over how to bring safer light to the cities of America.
Early natural gas lighting systems in homes, for example, on occasion were quite dangerous. They had no shut-off valves, so if the lamp went out, the gas would continue to accumulate in the home, and they had some major explosions in homes.
In 1879, Thomas Edison invented the first commercially practical incandescent lamp with a high-resistance filament that glowed when heated by a low current. He soon followed this with designs for a complete distribution system for light and power. On September 4th, 1882, after delays and cost overruns, Edison opened the first electric utility, the Pearl Street Station in the heart of Lower Manhattan's financial district. Edison knew that his product was going to be expensive and would need to reach many customers.
The whole reason for Edison's Pearl Street Station in New York City in 1882 was to demonstrate that electric technology could be used on a widespread basis, not serving one customer like steam engines in old factories, but many, many customers.
Edison's choice of direct current technology at Pearl Street limited his power plant's range.
The major disadvantage to direct current power in power plants at the time was you could not transmit electric power very far without losing a tremendous amount of the current. So you needed a power plant, every half mile or mile throughout the city.
Edison's main competitor, George Westinghouse, saw that electricity's future was in long-distance transmission. Westinghouse put his company, Westinghouse Electric, to work at perfecting a system using alternating current, which flows in reversing waves which propagate more easily and with less resistance in a transmission wire.
Beauty of alternating current is that you can generate that at a very high voltage and then step it down essentially to any voltage that you need. So you could step it down to a very low voltage that somebody would need at a house for their lighting, or you could step it down to a somewhat higher voltage that some business might need or some factory would need.
George Westinghouse purchased several vital alternating current patents from Nikola Tesla, a Serbian-born inventor. Westinghouse recognized Tesla's genius and brought the inventor to Pittsburgh to work for him. Together, they designed the components necessary to alternating current's success.
In 1887, George Westinghouse invented a meter for alternating current. He thought if you were going to make alternating current commercially available, you were going to have some way of measuring what you're going to sell to your customers.
Westinghouse's aggressive pursuit of alternating current technology put him in direct conflict with Edison.
It was a battle of business and technological giants, Thomas Edison versus George Westinghouse. This is called the Battle of the Currents, and it was essential because the technology that won would dominate the industry for the remainder of the foreseeable future.
With so much at stake, it's not surprising that the Battle of the Currents took a bitter turn. Edison went so far as to lobby New York State officials to have his competitor's product, alternating current, used to execute condemned men at Sing Sing prison.
I guess perhaps the lowest blow is when they were looking for a word to describe this. Today we say a person is electrocuted, but at the time they didn't have a term, and Thomas Edison suggested that they use the word Westinghoused, that the condemned man was Westinghoused. And obviously it's very, very upsetting to George Westinghouse.
But Westinghouse focused on the industrial competition at hand and left the courting of public opinion to his adversary.
There was a great World's Fair coming up in 1893 in Chicago, and they asked for proposals to illuminate the fair, to light it at night, realizing that nowhere in the world had a major event ever been illuminated at night before.
Westinghouse bid $500,000, half of what Edison bid, and was awarded the contract. He took advantage of the opportunity to promote his product.
So he installed a complete alternating current power plant that was on display for everyone to see. It had a giant Westinghouse alternating current switchboard, and the impressive part of that was that there was only one operator. One operator could control all the electrical equipment for the World's Fair of 1893.
67 million Americans and foreign visitors attended the Chicago World's Fair of 1893. Tesla and Westinghouse made sure that they left the fairgrounds with a good idea of who was winning the Battle of the Currents.
Both George Westinghouse and Nikola Tesla realized this was an opportunity to really showcase the potential of alternating current. One display, they had this huge word, power, and at night there were electrical currents, just like little bolts of lightning flashing all around this illuminated word.
After this dramatic success, Westinghouse was prepared for his greatest challenge, competing head-to-head with Edison for the right to build the largest power plant in the world. Niagara Falls. For hundreds of years, men had understood that the power of falling water could be converted into mechanical energy, the energy to run mills. But by the 1880s, there was open debate over whether the falls should be harnessed with this old technology or transformed into electricity and transmitted to industry and individuals hungry for power.
If we look at Niagara Falls and the potential for generating power, it was obvious to a lot of intelligent men at that period of time that there was a tremendous amount of power in the water coming down over Niagara Falls. If it could be harnessed, it could do great things for industry.
The International Niagara Commission solicited plans from leading engineers to design a plant that could transmit electricity to nearby Buffalo's manufacturing interests. This was a dramatic opportunity for George Westinghouse's alternating current system.
Ultimately, the decision to choose alternating current, which could be pushed much further distances over transmission lines from the powerhouse, won the day for alternating current.
It took from 1892 to 1895 to build the tunnel that would divert the force of the Niagara River to the plant's turbines. During the summer of 1894, electric cranes eased the 29-ton turbines, the largest built to date, into the wheel pits. The turbines were essentially windmill blades that could be driven by the force of Niagara's water. When the plant was finished, water flowed through the forebays and into the penstocks, vertical pipes about 8 feet in diameter. before entering and driving the turbines, which in turn spun rotors beneath the generators. Inside the generator, a magnet spun, creating a magnetic field which induced an electric charge in a casing of copper coils, thus producing electricity. In 1896, the Niagara Power Station began transmitting power 17 miles to Buffalo, New York. But it wasn't until 1901 at the Pan American Exposition on the Buffalo Fairgrounds that the general public was able to witness a large-scale display of the wonder of long-distance electrical transmission. In order to transmit electricity over this distance, transformers at the plant increased voltages to 11,000 volts, 4 times the voltage of an 1891 plant that Westinghouse had built. Inside a transformer, an electric charge passes through one wire coil, inducing a higher or lower charge in another separate coil. Voltages multiply at the ratio of the number of turns in the primary coil to the number of turns in the secondary coil.
What the Westinghouse engineers understood very clearly was that large power plants, which could produce large amounts of electricity, which could serve larger numbers of people over a wider area, needed the use of transformers to increase the pressure of electricity, to be able to push it longer distances.
The Niagara Power Plant provided not only a technical blueprint, but also an economic model that would be duplicated time and again over the coming century. If you build it, they will come. Heavy industry, in this case, would congregate around a reliable, cheap energy source.
There was a fellow in Pittsburgh named Hall who had an early process for the producing of aluminum using electricity. So he moved his company from Pittsburgh to Niagara Falls when the power became available. That company went on to change its name to Aluminum Company of America, and as we know today, it's the largest aluminum company in the world.
It soon became clear as electricity flowed out of the Niagara Power Plant that alternating current was here to stay. After Niagara, even Edison abandoned DC for AC technology.
I think it would be very fair to call George Westinghouse the father of the modern power plant. He was the catalyst. He was the person that had the commitment for this 10-year period of time to pull the resources to make alternating current successful.
In the ensuing decades, improvements in the electrical engineering of turbines, generators, and transformers would lead men to dream of a bigger and better source of water power. This dream would culminate at Hoover Dam, 40 years after the first electricity flowed out of Niagara. At 726 feet in height, weighing in at 6.5 million tons, and forming a 150-mile lake, Hoover represented a stunning increase in scale to Niagara and is still one of the world's largest dams. Hoover's transmission voltage of 287,000 volts speaks to the engineering leap that had taken place.
A number of people compare Hoover Dam with the earlier Niagara Falls installation. The difference between the Niagara Falls of the early 1890s and Hoover Dam in the mid-1930s is the improvements in technology over that period of time. Larger, much more efficient generators, and most importantly, very high voltage or high pressure transmission systems. Whereas people 17 miles away from Niagara Falls could receive electricity in the early 1890s, by 1936 and 37, when power was coming out of Hoover Dam, it was going over 250 miles to Southern California.
In the decades between Niagara and Hoover, privately owned power companies flourished throughout the country. It did not take long for company owners to realize that consolidation was the only way to profit in an industry that required so much investment to build infrastructure.
Tom McCarter had been the Attorney General of New Jersey. His idea, which was very novel at the time, was to basically draw a line between New York City and Philadelphia and buy up all the municipal light and gas companies and traction companies that existed between those two major points. And by doing so, he was able to generate the critical mass necessary to go out and begin to fund the tremendous infrastructure that was going to be required to build the electric system.
It was also a major step in the growth of the transmission grid. More customers meant greater revenue, An expanding utility could afford the expense of running transmission lines, linking multiple plants into a regional grid. This system spawned the giant interstate power transmission grids that today cover thousands of square miles. Improved transformer technology and higher voltages meant electricity could be sent farther and farther.
By 1903, you had over 100,000 volt technology, which meant you could push that electricity 150 miles or more. By the early 1920s, you had 220 and 230,000 volt technology, which meant literally anything within a range of about 300 miles of the power plant could receive electricity.
The workhorse of this grid is the transmission substation, like this one outside Athens, Georgia, where the job of increasing and decreasing voltages is done.
Our network grid system is based on about 3 main voltages, and then we go to some lower voltages for shorter routes. But the network system is basically 500,000 volts, 230,000 volts, and 115,000 volts. The 500,000 volts is basically like an interstate system. It travels from state to state, and there's about 5-6 main arteries across the state. The 230 kV system is sort of like the U.S. highway system. There's more routes, but still not the largest number. There's the largest number, the 115,000, which is more like the state highway system. Carries power from town to town, all over the smaller towns, medium-sized towns, and to other areas to feed different loads.
Transformers at the substation alter the voltages so that electricity can be routed where it needs to go.
We're standing in front of the 230 to 115 kV transformer, the big box here. The transformer converts the 230 kV voltage down to 115,000 volts, and then supplies power to the 115 bus, which is then shipped out across the 115 kV grid.
Electricity flows along the 115 kilovolt power line and gets stepped down as it nears its destination, private homes.
This is a typical distribution transformer serving a home. Distribution lines either 12,000 or 25,000 volts. It's stepped down to 120 to 240 volts to feed the house for the normal television, lights, appliances, everyday use.
This kind of everyday use has fueled the demand for power throughout the century, as consumption and desire for comfort have grown. To meet society's runaway electrical needs, utilities built their bread and butter plants. Next, what eats 36,000 tons of coal a day and never needs a rest? On 2,000 acres in Barstow County, Georgia, sits the second largest coal-fired plant in the United States, Plant Bowen. Owned and operated by Georgia Power, the facility produces in 15 seconds all the electricity a home will use in a year. With the exception of hydroelectric power in water-rich states, most of the country's electricity has been generated at coal-fired plants. In its heyday, coal was as plentiful as environmental concerns were scarce. Investment flooded into utilities, and coal plants grew bigger and more efficient.
Power plants went from small cottage industry to big, massive power plants. They were taking this steam cycle and really wringing every ounce of energy from it that they could, and doing so in a very efficient way. Basically, the way you generate electricity, you take water, and the simplest cycle is you boil it, and you create steam, and you pressurize it with this amount of heat that you're introducing into it, and you put it through a turbine. And the turbine is a simple fan, and as you introduce the high-pressure steam, it turns a generator.
But this simple steam cycle was wasteful.
It would take about 10 pounds of coal to produce the amount of energy that it would take to light a 100-watt light bulb for an hour. That's a very significant amount of coal. Today, through technological changes, we've been able to bring that down where now we're far under 1 pound of coal to produce the same amount of energy.
It took a combination of disciplines to affect this kind of fuel efficiency.
You had the power plant engineers refining that process, increasing the thermal efficiency, finding out how to use fuels in a more efficient way. You had metallurgists working on piping that were trying to bring temperatures up higher. You had boiler feed pump folks working on producing tremendous amounts of pressure.
All this to supply energy to a growing population and industrial base that demanded more power. Engineers call this demand load, and this load changes depending on the season and time of day.
Load is the electrical demand on our system. If you turn a light bulb on, that is putting a load on our system. It's putting a demand for the use of electricity.
The use of power goes up dramatically during the day, particularly today with air conditioning, so that you have very low levels of load at 8 o'clock in the morning. It goes up higher and higher in the morning period, and then about 3 o'clock in the afternoon, everybody's air conditioning is working at its maximum, industry is working hard, and that's the maximum peak load.
To service this energy cycle, a utility needs 3 types of plants.
You have base load, which is 24-hour load, and that's a plant that can run full-time. You have intermediate load, which is a plant that will cycle. It'll come on in the morning, and then at night it'll shut down. And then you have peaking facilities, which run really for just a few hours a day. And you need 3 different kinds of machines to cover those loads.
Plant mowing is what we call a base load power plant. The economics of operating it are such that it pretty well runs day in and day out, 24 hours a day.
It takes 4 9,000-ton train loads of low-sulfur coal arriving from eastern Kentucky each day to supply the plant. The coal is pulverized to the consistency of talcum powder before being blown into the boilers to be burned to heat water.
It's turned into steam that has a temperature of 1,000 degrees and a pressure of 3,500 pounds per square inch. This steam is delivered to a turbine. It turns a turbine. The turbine is attached to a generator. The generator and the turbine spin at 3,600 RPMs. That generates electricity, which we put out on our transmission line.
Once the steam has done its work in the turbine, it enters the condenser, where it flows over 36,000 copper tubes containing water from the nearby Etowah River. The river water absorbs heat, condensing the steam back into water so that it can be reused in the boiler. Hot river water is then cooled in 400-foot high cooling towers, each tower cooling 300,000 gallons a minute. Not surprisingly, it is no longer possible to find communities who will welcome a plant of Bowen's scale with its looming 1,000-foot high stacks. As a result, utilities like Georgia Power have developed peaking facilities with much smaller footprints, both in terms of land use and environmental impact. Combustion turbine plants like Plant Dahlberg in northeast Georgia burn natural gas or fuel oil instead of coal in what is essentially a souped-up jet engine. The gas turbine engine uses hot air and not steam to produce electricity. Fuel mixes with air, is burned, and the expanding gases drive the turbine. Once the turbine spins, the process is much the same as in a steam cycle plant.
The technology for this type of unit with the combustion turbine is very similar to what you would see on a jet engine. The jet engine has a compressor, brings air in, compresses it, burns it, and produces the power they use in thrust. This is a much larger machine doing the same thing. It has been equated to a jet engine on steroids.
Plant Dahlberg's 8 units combined produce about 600 megawatts of energy, less than the output of a single unit at Plant Bowen. As a result, the turbines are only used to produce supplemental electricity when it is needed.
It's used to provide energy to get you through the high demand period of the day.
Today, the energy market and societal pressures for safer, cleaner power have created a demand for smaller plants that are more evenly distributed on the landscape. This is changing the shape of an industry whose motto had always been, bigger is better. Built during the years that followed the Depression, those bigger plants produced more power, but in the 1930s and 40s, rural farms had no way of tapping into that power. Remote, expensive to reach with transmission lines, they simply were not on the grid.
Investor-owned utilities primarily did not want to go to the cost of providing electricity to rural customers, because you would face the cost of building power lines, in some cases 100 miles long, that would only serve maybe 4 or 5 customers. No return on your investment.
President Roosevelt and the Congress established the Tennessee Valley Authority in 1933. and the Rural Electrification Administration in 1935. The agencies shared the goal of bringing electricity to rural America, where only 10% of farms had power.
The TVA ostensibly began as a flood control effort by the Army Corps of Engineers, but it was quickly used as a way to find new sources of hydroelectric generation on the rivers of the area.
Dams were built, ultimately totaling 42 in the system, and a massive hydroelectric power project was launched, which grew to a total capacity of 4 million kilowatts by the 1970s. By this time, the mission of the REA and the TVA had been accomplished. 98% of all farms in the United States had electric service. Once the TVA had exhausted the hydroelectric possibilities of the river basin, administrators turned their attention to other forms of power.
In later years, the TVA moved away from its hydroelectric base and actually was a pioneer in the scale-up of some of the coal-fired boiler technology that we see today, and became a diehard proponent of nuclear power in the 50s and the 1960s.
Next, the half-life of nuclear power. How a technology grew up and got old before its time. In 1942, Enrico Fermi created the first self-sustaining nuclear chain reaction in a lab hidden beneath the football field at the University of Chicago. And in doing so, launched the atomic age. In an atom bomb, a sufficient quantity of weapons-grade plutonium is imploded by a TNT charge, initiating a chain reaction or fission explosion.
Fission is the process in which natural elements that are radioactive in nature, like uranium, is bombarded with neutrons, and then by bombarded with neutrons, they split into other elements, and when they split into other elements, they release energy.
Fortunately, not all nuclear reactions end in devastation. It was the peacetime harnessing of atomic energy that spawned the nuclear power industry.
The first privately financed and commercial nuclear power plant that was built without government help was the Dresden 1 facility outside of Chicago in 1959. If you think of the Manhattan Project and the atomic bomb and the ending of World War II, that the advancement in that technology over a 10 to 15 year period was pretty dramatic.
Today, more than 100 nuclear power plants are operating in the United States, supplying 20% of the country's energy needs.
San Onofre is what we call a baseload power plant, which means it tries to operate 24 hours a day, 365 days a year at full power output, which in the case of each of these reactors is a little over 1,100 megawatts of power.
The San Onofre Nuclear Generating Station in California's San Diego County supplies energy for 2.5 million homes and businesses.
Fuel is uranium. Uranium has the natural ability to fission, which means that the nucleus of the atom of uranium can literally tear itself apart. When it does that, it releases a tiny amount of heat, but what it also releases are additional neutrons. Inside a pellet of uranium, there would be billions and billions of atoms. So in very short order, we can get a chain reaction going in the uranium. So when you have 1 billion atoms releasing a little bit of heat, it becomes a large amount of heat.
This heat is released inside the nuclear reactor, which is housed inside a containment dome.
The walls are 4.5 feet thick concrete and steel, and in theory would be able to survive any man-made or natural disaster, earthquakes.
In this stress test, the wall withstood a direct impact of an F-4 Phantom jet. The reactor and its circulating system are filled with water, which submerges the fuel core.
If you were to put a thermometer on the core, the fuel assembly itself, it would be in excess of 600 degrees. As the water circulates by that hot uranium, the water gets hot, it comes out the other side, and it goes into 2 very large devices called steam generators. The steam drives the mechanical turbine, causes it to rotate at 1,800 revolutions per minute. That in turn turns an electric generator, and electrons are forced through wires, making electricity to do power to run homes and businesses.
The row of turbines and the generator together weigh in at 800 tons, or the equivalent of 800 Volkswagen Beetles. But despite this massive scale, it's still a fundamental process. As radioactive water from the reactor flows through the steam generators in a closed system, it heats clean water in a second closed system before it returns to the reactor. The clean steam drives the turbine and is then cooled by ocean water before returning to the steam generator, where it will again be turned into steam.
Behind me over here, obviously, is the Pacific Ocean. And about 3,200 feet offshore, we have a 16-foot in diameter pipe that's in the ocean. And when we turn on the pumps, we draw in about 1.6 million gallons of water per minute.
The pumps are run by 4,000 horsepower motors. That's the equivalent of 6 NASCAR cars running at full speed. Each pump is capable of draining an Olympic swimming pool in 15 seconds. If for any reason engineers needed to stop the nuclear reaction, they could do so by lowering an array of control rods into the core. The control rods absorb the atom-splitting neutrons that are driving the chain reaction, bringing it to a halt. But the surprising aspect of this plant is that, to a great degree, it runs without stopping.
It can run for 2 years without needing new fuel at full output. San Onofre Unit Number 2 has been operating for about 530 days consecutively. If this was a natural gas plant or an oil plant or a coal plant, we'd constantly be needing to bring in trains or pipelines bringing in this fuel product.
Outside, transformers step 22,000 volts of electricity up to 220,000 volts, essentially pressurizing it for transmission throughout Southern California. Although nuclear power is a relatively new and seemingly successful technology, it has yet to recover from an accident in Harrisburg, Pennsylvania.
The most significant event from a safety standpoint that has ever happened in the U.S. nuclear power industry was the 3 Mile Island accident in 1979. This was literally a brand new reactor with brand new operators. 4 o'clock in the morning, because of a combination of human error and mechanical design, they allowed the reactor's core, the uranium, to be uncovered for several hours. Without any water to keep the uranium cool, the uranium overheated and actually melted.
Evidence suggests that fallout from the accident was low, but the public relations setback was immense. No new plants have been built since. However, most nuclear power advocates predict that the industry will stage a comeback.
In my opinion, there will be a rebirth of nuclear power. It's not a question of if, it's a question of when.
And proponents suggest the question of what kind of waste we want in our environment may well be nuclear power's most convincing argument.
Nuclear power in the United States supplies about 20% of the electricity in the whole United States. That would probably surprise most people that it's that high. In that 20%, that avoids, in a yearly basis, the emission of about 177 million metric tons of greenhouse gases that would be emitted into the atmosphere if that 20% nuclear power was replaced, say, with coal or oil.
I would say that in the next 10 to 20 years, you will see the percentage of nuclear power rising, because that's a good way to address the global warming issue, and you do not have any solid waste other than the radioactive waste that you have to deal with. But I feel like we'll figure out a way to manage that problem.
Perhaps. But the 3,000 tons of spent fuel that the industry produces each year has no permanent home and is simply being held at the nuclear plants that produced it. Since this waste will remain radioactive for thousands of years, it's not surprising that most elected officials continue to say, "Not in my backyard." Next, electrical consumption grows as interest in conservation wanes. How will power plants of the future meet the demand? Although the history of power plants is largely one of growth and technological triumph, the future of electrical generation could not be more uncertain. What is clear is that we have come to a crossroads where environmental concerns, unchecked consumption, and technological limits meet.
The size of a power plant really has capped out at about 1,000 megawatts. And I was thinking about why that's really the limit. The boiler in a coal facility right now is the size of an apartment building. It's 11 stories high. Right now you've got turbine blades that in some cases are 14 feet long. And the tip speed of something 14 feet long, rotating at 3,600 RPM, starts to get supersonic.
Today, the country's electrical needs are supplied by regional interconnected power grids that in theory ensure that power flows where and when it is needed. In practice, these grids are straining to meet demand.
It's really a series of regional grids at this point. I mean, theoretically, you can move power from Texas to California. However, there might only be one really good path to do that. But ideally, you would want to have more options than that.
The lack of options in routing electricity is further complicated by heavy demand in summertime that is beginning to cause power shortages.
It's an issue of generation. It's an issue of not having enough kilowatt hours in the system. And it's occasioned by catastrophic failures at a facility or even small problems that take it offline for several hours.
The flip side of insufficient power generation is a countrywide lack of interest in energy conservation.
I see probably less emphasis and care about energy efficiency today than I ever have. I can't even get, people that I know and whatever to turn off their lights when they don't use it. Right here in my office here, I can't switch off the lights in my own office. It's or in individual rooms.
Over a third of the world's population doesn't have electricity today. And there aren't people looking to not have electricity, so it's always more load coming on globally. Well, we got to ask ourselves as a society or as creatures of the earth how we're going to give that load. And it isn't going to be burning fossil fuels.
When you talk about the environmental implications of power creation, you first have to look at the type of primary fuel. I mean, if you're talking about oil, you're dealing with NOx or nitrous oxides, you're dealing with metals that are in the oil. And when you deal with coal, of course, then you're dealing with particulate emissions, in some cases trace elements of heavy metals, and you're dealing with particulate emissions, which is almost the dust that comes out of the coal.
The immediate health risks of heavy metals and particulate emissions pale in comparison to the global implications of increased carbon dioxide in our atmosphere. Carbon dioxide, which is a direct result of burning fossil fuels. Concentrations of this greenhouse gas have increased sharply in the upper atmosphere since the beginning of the Industrial Revolution, warming our environment and threatening catastrophic climate change. In the face of a deteriorating environment, we clearly need to exploit a clean energy source. But which one?
The Earth's core is much hotter than the Earth's surface, fortunately, and the interaction of these temperature gradients comes very close to the surface in many parts of the world, and that can be used to create a hot fluid or create steam, which then drives conventional turbines.
At a geothermal plant, wells are drilled hundreds of feet below the Earth's surface into reservoirs with temperatures of 180 degrees Celsius or more. Although Mother Nature supplies the heat, geothermal sources like geysers are neither widespread nor are they clean.
Fraught with problems in terms of, first, it's tough to locate. There is none in the Northeast that I'm aware of, so we have difficulty using it here.
With a geothermal facility, your primary pollutant is hydrogen sulfide. So the problem there is taking the hydrogen sulfide out, capturing it, and then finding some way to deal with that once you've captured it.
The most futuristic of technologies, fusion, combines two light atomic nuclei to form a single heavier nucleus. This generates heat levels similar to the plasma state of the sun.
That's a dream for egomaniac scientists who figure that they can take the absolute most cataclysmic forces that be known to man and manage them.
There is, however, a less dramatic way to capture the energy of the sun: solar power. But the debate surrounding it is about efficiency, not safety.
Even in areas of the country where the sun shines a lot, like in the desert Southwest, the technology is still very behind in being able to supply the big base load plants that, like coal or nuclear plants. For an example, to replace an average nuclear plant would take about 600 square miles of solar cells with today's technology.
Solar advocates say that it is not so much the technology, but the concept of massive centralized power plants that limit solar's effectiveness. Perhaps the power plant of the future looks something like this. A house on the Maine coast that generates more energy than it consumes.
This house incorporates both solar thermal for space heating and hot water and solar electricity for electrical production. The panels are integrated to form the finished weathering skin of the south roof, and the house pretty much exists in terms of its heating, hot water, and electrical energy requirements from the harvested energy that falls on the roof.
The house does more than just exist. It contributes to the energy needs of its community. And homeowner William Lord is quite proud of this fact.
We make most of our own hot water and all of our electricity. In fact, we generate more electricity than we actually use. So the process of fitting into the environment is seamless in our case and is not disruptive.
Solar power not only makes environmental sense, but economic sense as well.
We have 2 meters on the house. One measures the excess energy that we export to the power company, and the other meter measures what energy we take from the power company. And in Maine, we have something called annualized net metering. And the bottom line is that we essentially pay no electric bill annually. When we built our solar house, we didn't realize we were actually creating an event. We added to that event a place where people come to learn about solar power. We have many visitors here. We added to that event our website. The Maine Solar House gets more than 1 million hits a year. This month I'm taking a look at a house in Kennebunkport nearby. The former President of the United States, George Bush, has solar thermal panels on his roof.
I think that's a great hope for everybody because clearly that is probably the best way to produce power. Taking incident solar energy doesn't pollute anything.
The direct conversion of solar energy into electricity with photovoltaics is the most environmentally benign method of making electricity. And so that, coupled with other conversion measures such as wind energy conversion, hydropower, can combine to gradually displace the conventional systems to build a resilient energy economy based on renewables. It's not a question of if, but when. And from my perspective, time is short. We should be investing the relatively plentiful and relatively inexpensive reserves of conventional energy to build this technology bridge to the future, because these are finite resources and they are not going to be here indefinitely.